confidence interval, it is equal to 1.65. So what happens is the Q value and the Z value in the book were coming as same as 1.65. So we will not take this as a 90% confidence interval. We will say that we want to create a 95% confidence interval of these VAR estimates. Okay, so we want to create a 95% confidence interval. In this case, what will the value of Z alpha? It will be 1.96, right? So 95%. So this will be dependent on what confidence interval you want. So your Z alpha will be 1.96. Now what they are saying is you need to assume about a width. Okay, so this is known as a bin width. Bin width is taken. So what you have is the VAR is taken at 1.65. So you will assume around this VAR. So you will say, okay, this is half of bin width and this is half of bin width. So what we are saying is, if I assume the bin width to be 0.1, okay, this value will be what? It will be 1.65, okay, minus 0.1 by 2, okay, which will be equal to 1.65 minus 0.05. So it will be 1.6, okay, and if I take this, it will be 1.65 plus 0.1 by 2, it will be 1.7. So what we have is, we will get a value of Q. Okay, so Q, what we are saying is, okay, so it will be depending on the bin width. Okay, so the bin width is 0.1, so we have 1.65. So we have actually it is minus. Okay, so it should be minus 1.6 should be here and minus 1.7 should be here. So this is what you have, is you have created a width around this. So it is based on your assumption about this bin width. This is your chosen value. You can make it any. Okay, so in the book they have taken as 0.1. Okay, now what happens is, after you have taken this bin width, you need to compute a probability which is given as P. Now how do you compute the probability P? So we have said that this is minus 1.7. So the probability P is this. So the area under the curve, which is from minus infinity to minus 1.7. Okay, and you have to measure another probability. Okay, so which is probability of this right side. So think about what we are doing. We are measuring this and we are measuring this probability. We mention this as R. Okay, so R is the probability of the area under the curve when this is greater than minus 1.6. Okay, so once we have computed this P and R, we will try to compute a function which is given as FQ. Okay, please note that this FQ is actually the probability of this. So this is FQ. Okay, so what will be FQ value? We know that P plus FQ plus R. What will be this value? P plus FQ plus R will be equal to how much? We know it will be 1 because it will cover the entire normal distribution, right? So your FQ will be equal to 1 minus P minus R. Is it clear? Okay. Please pay attention. So this is your FQ, right? So this is your probability of this area. Now what we are saying is, the standard error formula as per the book, it is given as this. Okay, it is P into 1 minus P divided by the bin width. Bin width is given as H, okay, divided by F of Q. So this is what they are taking as the standard error measure. Okay, we do not have to worry about any of this thing. However, we need to know that what is the impact of this standard error. Okay, so what will happen when the standard error, how it will increase or decrease. Okay, so depending on your choices, okay, of these values, your standard error will increase or decrease. So what we'll do is, we'll compute this P value. So probability, how you will compute? You will have to find out what is this P. So what will be the value of that P? We can put it in Excel. We can say norm S inverse, okay, and we can put minus 1.7. So we'll get, sorry, norm S dist. So we get 0.04456. So what I will say is, P P value is 0.045, right? Similarly, we can get value of R. We will say that it will be okay, so it will be equal to 1 minus this 0.945. So your R will be equal to 0.945. Right? In this case, your FQ will be equal to, okay, so it will be, right? So your FQ will be equal to 1 minus this. I'm sorry, I did some mistake here. Okay, yeah, it should be equal to, sorry, norm S distribution minus 1.7. So this is your value of P, this is the value of Q, and this is the value of 1 minus P minus Q, which is 0.01. So your FQ is equal to 0.0102. This is the value of FQ, right? And this is H is the value of, this is your bin width. So what will happen is you will compute this standard error. Okay, so how you will compute? We'll say that it will be equal to SQRT. Okay, it will be P into 1 minus P divided by bin width we have taken as 0.1. Okay, and okay, so this, okay, actually I should have, and this divided by your FQ, which is this, right? So this standard error comes as 6.45. So your standard error has come as 6.45 as the value. Okay, just I have to check whether this was entire thing was under square root or not. Okay, I think yeah. So 6.45 is your standard error. So what we are saying is your confidence interval. Okay, how you will be computing your confidence interval? It will be computed. So your standard error is known. We'll go back to this and we'll say Q minus SC into Z sigma or Z alpha. What will be the value of Z? Z is, we know it's 1.96. So we'll know that Z value is 1.96, and so this is the Z value. The Q value is 1.65. So we'll say that the confidence interval will be 1.65 into Z this, and it will also be equal to, we have to do the plus, right? So what happens is your var estimate is from minus 10 to 14, okay, which is a very wide estimate as of now you have got. Okay, so you are saying, okay, var is minus 1.65, but in reality it is between this and this range. So this is how you would create the confidence interval for the var. Okay, so for that you need to know this standard error. Okay, now we need to understand some implication. Okay, so let us see what are the implication that we need. Okay, so here I have not. Okay, what happens is, if you think about it, what will happen if you increase this width H? Okay, so if you increase this width, this will increase. Okay, so as a result standard error is going to reduce. Also what happens is, if this increases, okay, if this H increases, your P will reduce, all 1 minus P will increase. Note that this function P into 1 minus P, when it will be maximum, it will be maximum at P equal to 0.5. Okay, otherwise it will decrease. Okay, so this is what happens at 0.5, it will be the maximum. At other values it will be lower than this. So what will happen is, if you increase the bin width, your standard error will reduce. Okay, however, it is because this is reducing, this is increasing, also FQ is increasing. Remember this FQ, it will increase, it will become wider. Okay, because this is reducing. Okay, and this has also reduced. Okay, as a result this becomes wider, so standard error becomes lower. So bin width If it is increased, your standard error reduces. If bin width is decreased, your standard error will increase. Okay, so this is one of the thing that you need to know. Okay, right? And then about like obviously about your other things like Q, then Z, all it will all depend on you, on those values. Please note that we are not required to do any computation. Just I have given you the approach that is taken by the book. So when you are going through it, so you will understand the process. Okay. Now one other aim statement is they are saying that describe the use of QQ plot. It is called as quantile plot for identifying the distribution of data. Okay. So what happens is this plot is very useful in understanding how the data looks like. Okay. So what happens is many of the time when you are looking at data, you will try to hypothesize something about the data. Okay, let's say the data is a normal distribution, or data is a t distribution, or any of the thing, or many times you will not hypothesize it, but you would want to hypothesize. Let's say you want to hypothesize a t distribution as normal distribution. Okay, in fact in reality it will not work, it will not be the same, because there will be some presence of fatter tails. Okay, now many times you do not know about the underlying distribution as to how the distribution underlying is. So what we do is we plot this QQ plot. Okay, on the QQ plot, the x-axis has the normal quantile. So on x-axis you will plot the normal quantile. So if you see this 0 means like the 0.5 value, right? So here you will plot the normal quantile values. So 4 is roughly close to 1. Okay, so these are the values 1. So what we are saying is we'll plot the normal values over here. Okay, and on this y-axis you will plot the distribution which you want to judge. So here you will plot the empirical distribution. Okay, so this particular table, this particular graph, again I have taken from the book. Okay, here what the author has done is he has plotted on this y-axis the quantile taken from a normal distribution. Okay, but only 500 samples are taken from there. Okay, so when you take only 500 sample, so in reality you do not have actually covered the entire distribution. So what you find is, okay, so there is slight differences in this. If assume that this is also a normal and this is also a normal, it will exactly come a straight line. Okay, all the data will be exactly matching. Why? Because 0 will match with 0, -1 will match with -1, -3 will match with -3. However, if the distribution are not exactly the same, you will see that this kind of some data which are away, because this is 500 sample size, it will not exactly match. Most of these values which are near the mean are actually matching, but these outliers are not matching. This is the empirical quantile. So this is a normal distribution, a part of normal distribution is taken. Okay, the next diagram is on, this is the normal quantile, but this is the t distribution data. Okay, so these are the t distribution data. See the distribution. See what happens is over this area we can say that the t distribution behaves as if it is a normal distribution. Okay, over this, but at extreme what happens is t distribution has fatter tail. Here it has fatter tail, right? So what happens is over like any standard deviation when it is greater than 2, you find this significant, right? So what we have is on the y-axis it is t distribution is plotted, on x-axis you have the normal, right? Ideally if you are plotting normal versus normal, this will be the idea, right? Now what is the uses of this QQ plot? Okay, the QQ plot is done to get an understanding about the empirical data distribution. Okay, if you see that empirical distribution is very widely dispersed like this, then you will not assume the normal distribution for that, right? Because we are covering this topic which is a parametric distribution, you will not assume them to be a normal distribution, and you will see, you will go with some other method to estimate these risk measures. Make sense?